we will get live and then we'll wait for let's do sound check. Sound check, sound check. Yep, sounds on. Okay, so clock, 3 hours. Wait for Twitter to play catch up and we'll get started. Right, we're about time, so let's hit the go button on X. and we'll be ready to start. Right, X is up now, so I guess we can get started. Let's move this up a little bit out of my way. Let's get screen. There we go. Everything's live, everything's ready. Oh, hold on a minute. There we go. So I was just trying to get live chat back. Nobody else anywhere? Nope. So, it's almost finished. Right, let's get cracking then. I think, to be honest, we could probably smash through quite a few of these tonight because I don't think they're going to be nearly as, well, hopefully not nearly as difficult as an out of my comfort zone compared to the sorting algorithms and stuff, because that was some real doozy stuff. So, introduction to data structures. So, starting with this chapter, we're going to focus on how we can store and organize data in a way that allows for even better algorithms. Data structures are just organizational tools that allow for more advanced algorithms. Some examples: stacks, last in, first out; queues, first in, first out; linked lists, a chain of nodes efficient for inserts and deletes; binary trees, a tree where each node has up to 2 children; red-black trees, a self-balancing binary tree using colors; hash maps, a data structure that maps keys to values; tries, a tree used for storing and searching words efficiently; graphs, a collection of nodes connected by edges. So assignment: implement the count marketers function. It should accept a list of strings, job titles, and return the number of users who set their title to marketer. Locked-in users sometimes use different casing in their titles, so make sure to account for that. Should accept a list of strings and return the number of users who set their title to marketer. Okay. So just return can you do like a filter on a Python list? Like how do you filter? So we do list. Actually, around that we do length. So we do length, list, filter, and then we do so we have a function and then job titles. How do you do a filter? Oh, the lambda. I was trying to remember the lambda thing. So like that. So it would be job title, I'll just do equals marketers for now, but I bookmarketer, whoops. Well, it needs to be case insensitive. Lowercase Python check case insensitive. Just do 2 lower. Or lower. Okay. Lower. Yep, that worked. Right. That's fine. Let's see what they put. I should do that more often. Look at like the solutions that they publish, so I can sort of like see the difference. So I did a one-liner. They did a thing with a loop. It's fine. Doesn't really make much difference. So what are data structures? A data structure is a data organization, management, and storage format that enables efficient access and modification. More precisely, a data structure is a collection of data values, the relationships among them, and the functions or operations that can be applied to the data. So Wikipedia definition. In other words, stuck. In other words, a data structure stores data, organizes data so that it can be easily be accessed and modified, contains algorithmic functions to expose the ability to read and modify the data. You're already familiar with some of Python's built-in simple data structures: list, an ordered collection of items; dictionary, collections of key value pairs. Data structures store data and allow access to it efficiently. Don't use algorithms. Web-scale databases are only used by CS professors to scare business majors into dropping the class. Well, maybe the last one as well, but which is not a data structure. Tuple, MySQL, dictionary, MySQL. Lists, okay. So what is it? Lists, lists and list quiz. Okay, we know what lists are, but from a data structures and algorithms perspective, what are they good for? Let's break it down by operation. Append. Append an element to the end of a list. Cars.append forward is on average O of 1. We go directly to the end and add the element. Index. Accessing the element in an index. Cars2 is O1. We go directly to the index and return the element. Delete, removing an element from the middle of the list. Cars.pop2 is ON. We have to sift all the elements after the deleted element down one index. Searching for an element in the list. Cars index forward is ON. We have to iterate over the list until we find the element. In other words, lists start to struggle in 2 primary areas: when you need to frequently delete items from the middle of the list, when you need to frequently search for specific elements in the entire list. So assignment, we need to display a user's last job title in their profile. Implement the last work experience function. It takes a list of our users' work history strings and returns the last place they worked. Assume the list is ordered from oldest to most recent. If the list is empty, return none. So I think it's just simple as if length of work experiences equals 0, then return none. Otherwise, I guess return work experiences 0. Or the most recent, so I guess -1 like that. There we go. Oh yeah, just -1 goes to the back of it. Let's have a look at their solution, see what it was. Yeah, did the same thing. List quiz. Answer the questions based on this code from the last assignment. So looking up an item in the list by index is much faster than searching for it using iteration O1 versus ON. What is the big O complexity of last work experience function? Where n is the length of work experiences array? O1. Just go straight to the index. Why is index lookup so much faster than iteration? The index is stored in the back of the physical book. And as we all know, turning pages is blazingly fast. The computer can jump straight to the location of the index. An index is like an address of the item in the list. An index lookup just requires scanning the array up to the given location function. It's just jump straight to the index, right? Stacks. Okay, so stacks. A stack is a structure that stores ordered items. It's like a list, but its design is more restrictive. It only allows items to be added or removed from the top of the stack. So let's see what the video is like.
Computer science students really overthink stacks. They're just about the easiest data structure to learn, though, so honestly, don't stress about it. Imagine you're at a salad bar, but before you load up on bacon bits and croutons, you need a plate. Now, it's a self-serve situation, and you notice a giant stack of plates sitting on the counter. Do you grab one from the bottom? The middle? No, because you're not a complete idiot. You grab one off the top of the stack. Okay, but here's the thing.
Some of them are idiots.
Partner who you're out to dinner with, and they explain they have to leave, and you decide you just don't even want salad anymore. So, do you lift the giant stack of plates and shove your plate back at the bottom? Stuff it into the middle? Again, no, you're actually a sane human being, so you just set the plate back on top of the stack. And that's it. That's how stack data structures work. You put items onto the top of the stack, one at a time, and then you remove them off the top again, one at a time. Once something has been pushed down to the very bottom of the stack, you actually have to take everything else off the top before you can get down to it. Stacks are last in, first out. LIFO. That makes them restrictive, but useful in specific situations where you're okay with that limitation. For example, undo or redo in a word processor, or the back button in your browser history. Those are real-world examples that actually use stacks under the hood. And the real benefit of stacks is that they're super fast. Pushing and popping items onto a stack are both order 1 operations.
Okay. Good explanation. I guess you could also call it philo. First in, last off. Just preference. I know it's called that for a reason, but anyway. Observation. It's called a stack because it behaves just like a stack of physical items. Imagine a stack of plates. It's easy to take an item off the top of the stack, but you can't really get to the items in the middle or at the bottom without removing the items on the top first. You'll often hear a stack referred to as LIFO, last in, first out data structure. Whoever decided to take the simple concept and slap a nasty acronym on it should be forced to program Prolog for the rest of their days. Assignment. In this chapter, we'll build a stack from scratch. A stack will be used at locked in when we need to undo/redo functionality. For example, a user can add other users to their connections list and then undo the last connection they added. Stacks are a great way to implement undo functionality. For now, we'll just focus on two methods, push and size. Notice that the stack class already has a constructor and underlying list that we'll use to store items. So complete the push method. It should add an item to the top of the stack. The top of the stack is the end of the list in our implementation. So it's just going to be self.items.append item, and then complete the size method. It should return the number of items in the stack. Okay, so return self.items. Oops, it's going to be a length, isn't it? That stack speed. You might be wondering why would I use a stack instead of a list, or isn't this just a list with a few features? And you'd be right, a stack is a list with a few features, but that's the point. By restricting the ways that we can interact with the data, we guarantee that certain operations are blazingly fast. Here are all the operations a typical stack supports, along with their big O time complexity. Push, pop, peek, and size, which is going to be a push, add an item to the top of the stack. Pop, remove and return the top item from the stack. Peek, return the top item from the stack without modifying the stack. And then size, return the number of items from the stack. It's all O1. O to the order of 1. That means no matter how many items are in the stack, these operations will always take the same amount of time. Stacks are really fast and are usually the best choice when the behavior of a stack is all you need. So which operation is O1? Size, push, pop, peek, all of them. Where can items be added to and removed from a stack? Top. Oh, it is time. Right, and we're back. So, right, let's get back to it. Okay, so pop and peek. Now that we can add items to our stack, we need to be able to view the top item and remove the top item. Complete the peek method. It should return the top item from the stack without modifying the stack. If the stack is empty, return none. So peek. So if I guess we do self.size is equal to 0, then return. Whoops, I forgot the thing. Return none. Otherwise, return self.items peek top height of the stack. Just one like that. And then pop, complete pop method should remove and return. It should remove and return the top item from the stack. If the stack is empty, return none. Okay, so if self.size is equal to 0, then return none. Otherwise, return self.items, I guess, like that. Nope, not quite. Is there a thing for like Python, so like arrays or like lists? Append, insert. Move pop. Or I could just do pop on its own. Okay. Pop. 1 like that. Oh, oops. Hold on. How do I refer to in a Python class? How do I use other methods? Okay. Python class method use other method. Oh God. Oh, whoops. I've done the wrong thing. Self dot. Oh no, no, that was right. Hold on. We'll change it like this way, do it like that. So if it's greater than that, greater than not separated between instances of method and int. Have to be like that. Greater than or equal to, that can't be right. No. Oh, I'm a big dum dum. Just realised. I need to call it like that. Ugh. I'm really dumb. Where's it gone wrong here? So it's got non. Right, so it should be name David. It's not. Because Python, JavaScript, none. Got those last parts right. So is it this? Is it the needs to be the last one? Simple as that. Okay. Let's see their solution. Oh, they did it the way I did it first time. And they did it without the pop method, so makes sense. Stack review. So all supported operations are O1 by themselves. However, some tasks like getting to an item at the bottom of the stack have a higher time complexity because they require multiple pop operations. Stack operations are limited. No searching, no sorting, no random access. Stacks, like all abstract data types, can store items of any type. What makes a stack is the behavior of the operations, not the type of data it stores. Stacks are often used in the real world for function call management, undo redo functionality, expression evaluation, and browser history. What can be stored in a stack? Your mum's phone number, objects, integers, and any of these. Whoa, steady lane, go on now. Any of these. If you want to get an item at the bottom of the stack, where's the big O to retrieve that item? O n to the power 2 because plates are heavy and lane is weak, which is why he now writes codes instead of busting tables. Respectable. O(n) because all the other items need to be popped first. O log n because stacks can be searched using binary search. O1 because the pop operation is O1. Well, you have to pop everything else first, so it's that. So using a stack. Locked-in supports a basic scripting language. It allows technically savvy HR managers to write scripts that can automate repetitive tasks on the platform. The language makes use of parentheses to group operations together, and we need to be able to check if the parentheses in a script are balanced. So balanced parentheses. pretty sure I did this in a coding thing on my coding, challenge thing I did a long time ago. Balanced parentheses. So parentheses are balanced when each parentheses has a corresponding parenthesis, and the pairs of parentheses are properly nested. For example, balanced that and that, that and that, that and that, 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 that. Everything balances out. Unbalanced ones, one without, one with no opening, one with opening with no closing, and two in between. Unbalanced opening. So complete the isBalance function. It takes a string as the input and returns true if the parentheses in the string are balanced and false otherwise. Use an instance of the provided stack class in stack.py to keep track of the parentheses. You only need to consider the characters. Right, okay, so complete the isBalanced. If the string are balanced and false otherwise, use an instance to provide the provided stack class in stack.py to keep track of the parentheses. Okay, so I've not used the stack thing. Oh wait, hold on, we can see what it looks like. All right, okay. Well, I guess returns proof the parentheses string are balanced and false otherwise. Use. Okay, so I guess if we just do a simple thing of can just do something like input stack equals stack, and then give it input string. And then we can just be if input stack dot size so if input stack dot size is forget how to do, is it like a modular equals 2, then print even else return false. Oh, what's the thing? Forgot to do it. Modulo operator. Oh, just a percentage, right? Okay. I suppose I need to split it. Self. Oh no, we can't. That's right. That's not what the stack's for. Right. Okay. Never mind. Input stack. So I guess if input string okay. So if it's an even number, right? So check if a number is odd. Okay, that just works by a fluke, but we need to basically be able to check. So this just checks if the input string is even, then we'll actually go ahead and do stuff. If it's not, then there's no way it can be balanced because you need at least an order of 2 for everything. So you need like 1 closing, 1 opening. So if it passes that, then it starts doing stuff, and eventually return true if it passes all the kind of checks. I guess. How do we check this? So is it balanced? So in, input, we call it input list equals input string. How do you split something into a list again? I forget, like a string to a list. String list. Oh, split and join. Hold on. Oh, I just do split, right? Dot split. So then I've got the list. So then for input input item in input list, I guess input stack dot, what was it? Not pop, push, push input item. So then after that's finished, we've got the whole stack. I'm not sure on this one. Like, so we want to track sort of. So when we start popping them, so if we pop, Let me think about it. Just kind of pseudocode it out. So like as we go through the list, what's the? I'm just trying to think. I feel like there's sort of like an easy way of doing this, but what's coming to my head currently is basically when we loop through the list the first time, we want to compare like. No, I was gonna say compare the first and the last, but that doesn't really make any sense. I suppose some sort of like running tally thing. So as um I mean it's not as simple as that, is it? It can't be. No, because you could have an even number but have the brackets in completely the wrong place. It's just all the examples they give are uneven. They don't give any even examples of like it being unbalanced. But you could have basically where you could start with a close, like close, close, open, open. It's like that's not valid. Hmm. Mainly what I was thinking was like if we loop through this, if we loop through the first time, something along the lines of as you add an opening parentheses, you increase like the, I don't know what you call it, like the some integer, some counter of some kind. So as you're going through, increase the counter when you hit a back a closing parentheses, then you negate it, and as long as at the end it's at 0, then everything balanced, right? So I mean, I don't even think we even really need a stack for this, but I'll just try it. So let me just try this. So counter, or should I say balance equals 0, and then I'd say so if balance equals 0, then return true, otherwise it's just a return false again. So as we go through there, so if input item is equal to open, then balance plus equals 1, else, I guess we just need else, don't we? Like they were saying it wasn't a thing, so minus equals 1. Will that work? Does it get to -1? Oh, I didn't split it properly. Uh, hold on. Python split string into Oh, you just use a list on it. That makes more sense. Okay, we'll submit. Let's. Whoops. I guess if. Whoops. Guess if input list 0 is equal to that, then return false. Oh no, which one did it fail on? One, two, three. Okay, so that one's not valid. Let's run that one through. So it is divisible by 2 because it's 3. So it goes through. Then we split it, and then I say it passes that because it's not an opening thing, and then balance is 0. So let's print the I guess balance and input item. Run that one. What's wrong with that one? So I move it down here. So yeah, we add 1, 0, -1, 0, 1, 0. I suppose it's in the same amount of brackets, but just not in the right order, in the right placing. Like if you swap those around, then they'd be right. Not sure how I check for that. This, I mean, I'm not using stacks, so, but I can't think how to use the stack to make this more efficient. and comparable. Um, I think I can fix this. I'm not sure. Check first and last. Second and second to last. How do you check it's sort of where its corresponding thing is? Like first and last match, second and second to last match up, but then third and third from last don't pair up. I suppose, do you just not allow negative numbers? Is that part of it in here? So my elif balance, if balances are not equal to minus not equal to 0, then do it like that. Passes, but I don't think that's the right way of doing it. Let's have a look at their solution. So they have a stack. So then for each character in input string, oh, you can just loop straight onto it. You don't need to put in a list, right? Okay. So then if the character is the opening parentheses, then push that on. Else, if the character is a closing one, if stack.pop is none, return false. Right, okay, return stack.peak is none. Okay. So I kind of get it. Right, queues. And we've got 6 lessons with this one. Queues, linked lists, binary trees, God, all the things. Oh, gonna be a bit of time to get through this one. Okay. So what is a queue? So a queue stores ordered items, again kind of like a list, but again like a stack. Its design is more restrictive. A queue only allows items to be added to the tail of the queue and removed from the head of the queue. It's called a queue because it behaves like a queue of people waiting in line to order coffee. In the Lord's tongue, American English, we say I'm waiting in line, but in the UK they say I'm waiting in a queue. Alan Turing was British, so we just gotta let them have this one. The first person to get in line is also the first person to be served. Get out of line, so you'll often hear a queue referred to as FIFO, so first in, first out day structure.
Queues are one of those data structures that you probably already understand, even if you don't know it yet. Have you ever stood in line for 2 hours just to be told that Mickey had to leave and couldn't meet your daughter at Disneyland? Well, if you have, you were in a queue. You might already know about stacks, which are last in, first out, and queues are very similar, but they're first in, first out. Queues tend to be used way more often in the real world than stacks because they perfectly model so many real world systems. Amazon packages on a conveyor belt that my wife ordered for herself when I forgot our anniversary, that's a queue. People waiting for the new iPhone that has the exact same features as the last one, also a queue. The 69 bugs in your dev team's ordered backlog, believe it or not, queue. Whenever items are processed in the order they are received, that's a queue. Now, queues have three main operations. Enqueue, which adds an item to the back of the queue. Dequeue removes an item from the front of the queue. And peek, which reveals the item at the front of the queue without removing it. Now, that kind of sounds just like a Python list, right? And to be fair, it kind of is. But we actually are restricting ourselves to just these three operations. No iterating or searching allowed, which we could do with the Python list. But it's this same restriction that's what makes queues fast. Just like a stack, they can have order one time complexity, both for enqueue and dequeue operations, assuming the implementation's good. That means queues stay fast, no matter how many items are stored in them.
Cracking explanation. So which example of a real world queue? The set of possibilities in a game of dice. The absurdly long line of millennials without children waiting to get into Disneyland. Lane's collection of totally cool and totally not lame Lord of the Rings action figures. Quack quack. A stack of plates at a cafeteria. So it's the Disneyland parable because he just mentioned it then, didn't he? So queue class. So assignment locked in uses a queue to keep track of the order that recruiters should use to reach out to job seekers. So implement the following operations on the queue class. So push adds an item to the tail of the queue, index O of list. So we'll do self.items tail of the queue, so append item. Pop removes and returns an item from the head of the queue, last index in the list. So return self.items dot pop, I guess we can just do that like so. -1 peak returns an item from the head of the queue, so return self.items -1, and size returns the size of the items in the queue, so return length of self.items. Note, you'll often hear words used interchangeably in programming. For example, here we're saying push, pop, but enqueue and dequeue are also common words for the same thing. So push, enqueue, adds an item to the tail of the queue. Pop, dequeue, removes and returns an item from the head of the queue. Let's run this and find out. Failed, whoopsie daisy. So it's going to be 0. Got the wrong end of the stick. Is that right? Oops. I think this one needs to be like that, right? Whoops. What happened? Platform entity list. Guess we gotta put those checks in again. So if self dot items self dot size is greater than 0, then do that. else return none. Oh. Same thing, I've got to do this check. Okay, so if self dot size is greater than 0, then that. Then return none. Huzzah! Okay, try to trick us with that. Queue speed. So how fast are queue operations? Well, in an optimized queue, they'd be push O1, add an item to the back of the queue, a pop O1 is remove and return the front item of the queue. Peak, return the front item of the queue without modifying the queue. Size O1 as well, because return the number of items in the queue. Just like a stack, all operations are O1. No matter how many items there are in the queue, these operations will always take the same amount of time. The reason to choose queue over stack is all about ordering. Queue should be used when you need to process items the first order they were added. LIFO stack versus FIFO queue. A problem. Our current queue class has a problem. Take a look at the push method. It's not O1. The list insert method has to shift all other items in the list down to make room for the new item. So insert onion into queue. So, yep. We'll solve this very solved problem soon. What is the big O complexity of push pop peak size operation when optimized? O1. Another question. If an item could be anywhere in a queue, what is the big O complexity to retrieve that item? OM, because you might have to pop all the items. And with anywhere in the queue, what is the big O to retrieve that item? OM, because you might have to pop all items in the queue. O log M, because using binary search can be used. O1, because pop operation is O1, blah, blah, blah. I have psychic powers, it's the first one. You might have to pop all of them to get it. Why is our list-based queues push operation ON? Because you have to search for the perfect spot to insert the new element, because you have to remove everything from the queue before you can add a new element, because you have to move all the elements over by one index to make room for the new element. Okay, so matchmaking queue. In locked-in, users are founding company. Users that are founding companies can join a matchmaking queue to find potential co-founders for their projects. We'll use the queue class we've built to manage the matchmaking process. Notice the search and remove method on the queue class in queue.py. It breaks the rules of traditional queue data structure, but will be useful in solving this real-world problem. It's okay to violate academic constraints as software engineers as long as we understand the trade-offs involved. Assignment. Complete the matchmake function that simulates users joining and leaving the matchmaking queue. The function should take a queue instance and a user tuple containing a name, an action, either John or leave. Join or leave. Sorry, I'm losing it. For each call to matchmake, if the action is leave, search the queue for the user and remove them if they're in the queue. Okay, so if I've forgotten tuples in Python. Come on. So tuple. How do you access the thing? So all right, just index into it. Okay, so if user one equals leave, was it? Leave. Then search the queue for the user and remove them if they are in the queue. Okay. Search and remove. Okay. Okay, so QUE dot search and remove, and then we go user 0. Okay, if the action is join, push the user's name onto the queue. Else, QUE dot push, or is it NQ? What have they called it? Push. Okay, say push user 0. Lastly, check if the queue has at least 4 users in it. If so, pop the first 2 users from the queue and return the following string. Okay. So if QUE dot size, why doesn't it have autocomplete for stuff? Size is at least 4 is greater than 4, then if so, pop the first 2 users from the queue and return the following string. Okay. If there were less than 4 in the queue, return the following string, no match found. Okay, else. Return no match found. So we'll say user 1 equals QUE, QUE dot pop. User 2 equals QUE dot pop. Then we're going to do return f string like that, I think. And it's going to be user 1 matched user 2. Lastly, check if the queue has at least 4 users in it. If so, pop the first 2 users less than or equal to. Okay. If there were less than 4 users in the queue, return the following string, no match found. Oh, missed exclamation mark. There we go. Huzzah! That wasn't too bad. Now on linked lists. 10 lessons in this one. Binary trees, red, black. Okay. Oh gosh, it's just a lane. This is a brutal module to get through, man. It just goes on and on. Right, here we are. Linked list, got 10 lessons on this one. So remember how the push method on our queue is on instead of o1? Yeah, let's fix that. Let's build a faster queue. We'll use a linked list instead of a regular list. So list array under the hood. A linked list is where elements are not stored next to each other in memory. Instead, each item references the next in the chain. Nodes. So our nodes will be represented by a simple class with two fields. Value, the raw string value that the node holds, Carl or James, and next, the reference to the next node in the list. So assignment, let's lock in and make locked in faster. Complete nodes constructor. Set its file field to the provided value. Don't touch below this line. So, self, I've forgotten this now. So self.val is equals to provided value. Okay, so equals val, I think it's that, and then self.next is equal to none. Complete the node set next method. It should take the next field to the provided node. Okay. So self.next equals node.val, basically. That's how it goes. Nope. Set next. Oh, excuse me. Say its next field to set its val field to the provided value. Next field to none. And then self.next to the provided node. Or just give it the full thing. Okay. Okay. Makes sense. Linked list versus list. So a linked list is a collection of ordered items. So it's similar to a normal list, also called an array or slice in other languages. Items in a normal list are stored next to each other in memory. And get an item and to get an item from a normal list, we have to use a numbered index. So provide reference, yeah. You can think of the index as simply an offset from the start. Oh, crazy. The cars list in this example refers to the start of the list, and 3 is just the fourth item in the section of memory with a normal list. With a normal list, all data is stored in the same place in memory, and the index is just a way to find the right spot. In a linked list, there are no indexes. Each node contains 2 strings, the data itself and a reference to the next node in the list. Iterating over a linked list requires starting at the head node and following the next references until you reach the end. Frankly, linked lists can be annoying to use in kernel overhead, so why use linked lists at all? It's because sometimes linked lists are much faster to make updates to, particularly when inserting or deleting items from the middle. In a normal list, if you insert an item in the middle, you have to shift all the items after it down one spot, which makes O at n time. So insert insert node in the middle, shift. In a linked list, once you traverse to a given node, insertion at O1, because you can simply update 2 references. So linked list, insert a node in the middle. Yeah. well, it doesn't really matter. You just change the reference, don't you? So you can find an item in a linked list by sending up your thoughts and press, popping an item off the list, iterating through all the nodes by the following the next references, indexing right to the item with an index number. No. You have to loop through them all. Yeah, so it's the same thing again. Linked lists have a faster time complexity and regular lists when it comes to iterating through the list, inserting / deleting items from the middle of the list, appending items to the end of the list, accessing items by index. So inserting, deleting items from the middle of the list. So iterating. Even though iterating with linked lists kind of sucks compared to simplicity of arrays, normal lists, we've got to do it. Although the implementation is more complex and slow, we can still make it easy for users of our class by providing the iter method, the yield keyword. So the yield keyword in Python returns a value kind of like return. However, it's used to turn the function into a generator function. Oh, excuse me. A generator function creates a new function object. When that function is called, it executes the code in the generator function until it hits a yield statement. At that point, right, hold on, let's read that again. A generator function creates a new function object. When that function is called, it executes the code in the generator until it hits a yield statement. At that point, the function pauses and returns the value of the yield statement. The next time the function is called, it picks up right where it left off. Okay, create message generator. Yield, okay. So gen create message generator. So next gen print first is hi. Okay. Second is next gen prints, right, okay. So every time you call create message generator, it creates a new generator instance. To continue from where you left off, you need to assign the generator to a variable like gen. Right. In the example above, this way you can use next to loop over the generator. You're continuing the next instance rather than assigning a new one. So assignment. The linked list class is a wrapper class that uses the node class we already wrote. So complete the init method it should set the head field to none. Self.head equals none. No other node points to the linked list head first node. So no other node points to the linked list head first node. So the linked list class itself needs to keep track of it. We'll use the term head and tail like this. Head node, 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 tail node. The direction flow above might feel opposite to what you're used to with a queue, but it's really the same. Above, I'm using arrows to show which nodes are pointing to which other nodes. In a future lesson, when we implement a queue using a linked list, we'll add elements to the tail and remove elements from the head. So complete the iter method. It should be a generator function that yields each node in the linked list from the head to the tail. So create a reference to the head node. Node equals self.head. Okay. So node equals self.head. Use a while loop to iterate over the linked list until the node is none. So while node is not none, then yield the current node, set node to the next node. So yield the current node. So now node equals, hold on. It says yield node, then set node to next node. So self dot next. Node dot next. Okay. So add to tail. Time to allow our linked list to add new nodes to the end of the list. Kind of like a regular Python list append method. So first node and last node. Assignment. Complete the add tail method. It adds a new node to the end of the list and returns nothing. Okay, so if there isn't a head node, set the new node as the head and be done. Okay, so if, hold on. So I guess if self dot head equals none, then set the new node as the head. Okay, self dot head equals node, and then return. Otherwise, keep a reference to the last node in the list. Start with it set to none. So last node equals none. Iterate over the linked list. So then for node in self.nodes. Update your last node reference to the current node. So I guess last node equals node. And then once you've iterated over your entire list, your last reference should be the last node in the list. I'll tell you use the next field of the last node to the new node. So okay, so set the next field of the last node to the new node. Last dot next equals update your last node reference to the current node. Once you iterate over an entire list, your last reference should be the last node in the list. The tail. See the next field of the last node. Set the next field of the last node to the new node. What? Oh, sorry, passed in, right. Guess just like that, is it? Uh-oh. That wasn't good. For node in self. Let me try again. Shouldn't think there's like an infinite loop here. Yeah, there's no way it should take that long, so what am I doing wrong? So if there isn't a head node, set the new node as the head node and be done. Otherwise, keep a reference to the last node in the list. Start with it set to none. Then iterate over the linked list. We built this already. Whoops. Set next. There isn't a head node, and set the new node as head and be done. Nope, that ain't it. Okay, then last node equals none. Keep a reference to the last node in the list. Started with it set to none. That's what I've done. So then iterate over the linked list. We built this already. Yeah, so iterate over it. And then update last node reference to the current node. self. So I'm going to call this self node because there's a clash of things here. Self node. There we go. Variable problem. So add to head. But added flexibility let's allow users to add items to the front of our linked list as well. So assignment. Implement that add to head method. It should add a new node to the front of the list and return nothing. Implement add to head method. It should add a new node to the front of the list and return nothing. Set the next field of the given node to the current head node. Set the next field of the given node to the current head node. So node dot what was it? Set next. Set next. Current head node. So current head, and then update the head reference to the given node. So self dot head node. Whoops. Easy peasy. Linked list queue. When do I get 2 questions? At the end. Great. So linked list queue, remove from head, and then these ones. Right. So linked list queue. So to use our linked list as a fast queue, or one pushes or pops, we need our add to tail function to be O1. Currently, it iterates over the entire list before appending an item. We can fix this by keeping track of the last item with a new data member tail. Note, it's common in algorithms to make this kind of trade-off. By using a little extra memory, keeping track of tail, we can make our operations faster. Sometimes you might need to go the other way and use more computation time to save memory. Assignment. So locked-in's queue was working just fine on small datasets, but appending items once the list has 100,000 plus items has started to take a toll on our servers. Implement these changes to speed up our linked lists insert O1. So add to head should set the tail reference to the given node if the list is empty. Add head should set the tail reference to the given node if the list is empty. Add to head should set the tail reference to the given node if the list is empty. So here, so like if self what is it, self dot size is less than or equal to 0, then should set the tail reference to the given node. So if the list is empty, so self dot tail, can we do that? Equals node. Whoops. So if length of self is less than or equal to 0. What? What list? Should set tail reference to the given node if the list is empty. Do we not have any size thing now? Just print what self is. I'm getting confused there. Should set the tail reference. To the given node if the list is empty. How do I check like the list? Like so self. You know, where's the node? So just self dot node is equal to none. Is that the deal? Ugh. Self dot. Add. So should set tail reference. Okay, yeah, that's what I was waiting for. So self dot tail equals none. So now actually run. Right, so add the tail. Set the head and tail to the given node if the list is empty. So if self is none, then self dot head equals node, and then self dot tail equals node. instead of iterating to find the, so then instead of iterating to find the last node, use the tail reference to append the new node. So iterate to find the last node, use tail reference. Oh. Update tail reference to the new node. Use the tail reference to append. Update tail reference. Instead of iterating to find the last node, use the tail reference to append the new node. Tail reference to append the new node. Instead of iterating, so where's it going wrong now? So non-type object has no value, attribute value. Then return, I guess. Is that the missing piece? So add tail should set the head and tail to the given node if the list is empty. Instead of iterating to find the last node, use tail reference. Use the tail reference to append the new node. Update tail reference to the new node. Done that. Done that. Instead of iterating to find the last node, use the tail reference to append the new node. So it's going to be wrong, but might as well try. So run that. Not working. Actual tail. So we get rid of that. Does that make any difference? Nope. Let's try and go back, see if I deleted too much. Okay, so we don't need... Don't want that. So it said instead of iterating to find the last node, use the tail reference to append to the new... To use the tail reference to append the new node. Like that. Instead, use the tail reference to append the new node. I just don't get the wording on that one. It's not quite making sense. Might need boots. Howdy again. What's wrong with my method? Wrong with my method. Not method. Go on, Boots, this time. First time tonight. I'll let it slide. Okay. So I see your latest code and the output error. Let's unravel this puzzle together, young coder. So the message says, non-type object has no attribute, set next. So It means self.tail was null at the time you tried to run blah 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 in add tail function. Let's use the Socratic method to consider if your add tail under conditions, in what conditions could self.tail be none when you reach self.tail set next node. Notice you have checks like set if, set else, self is none, and self.head is none in Python. In Python, will self ever be none inside an instance method? But the no, yeah, wherever. So it is your add to head logic for setting self.tail triggered under the right circumstances. I don't know, because I don't know the reference to the list. Like, how do I, I don't understand where the list is. So while node is not none, yield node. So self head, node in self. I don't know how to reference the list. I suppose that's not right, but you need to set both self-head and self-tail to the new node the first time you add to an empty list, both add to head and add to tail. What? Should set tail reference to the given node if the list is empty. Which conditions should you really be checking at the beginning of both functions if you want to handle an empty list? Try think about whether it's self that could be none or something else. But there's no init function on this, so how, where's the list? Right, go back to this one. Add to head. Should set tail reference to the given node if the list is empty. What do you mean? Like I'm a bit confused. Like what? So we're in a list, but we don't have lists stored. If the list is empty. I'm not sure. I don't understand that. I don't no. I don't understand the wording. How do I get the list? You're getting close, and the troublesome part is this line. In Python, self will never be none for an instance method, so that condition will never be true. What you really want to check is whether the list is empty. Here's a gentle hint with a question. When is a linked list empty? Which of its attributes would be none? Think specifically about checking if self head is none. At the start of both add to head and add to tail, if the list is empty, what two things should update? Give it a try, and what change could you make to your empty list logic to add tail and self tail is always set when you add the first node. So the first part should set tail reference to the given node if the list is empty. When is a linked list empty? I'm not sure when a linked list is empty. It's a great question. In most linked list implementations, a linked list is considered empty when its head attribute is none. No node means no head. Sometimes tail is also none, but checking head is standard. So ask yourself, when you add the very first node, the list is empty. What should both head and tail point to? None. You might want to rewrite your check to see if the list is empty by using self.head. Right, so, and then here, set the head and tail to the given node if the list is empty. Instead of iterating to find, let's use the tail reference. So I don't need that. Don't even need to remember what it is. Use the tail reference to append the new node. If it's empty, do I return there early? Oh, blimey, that was a headache. Alright, I got it in the end. Huzzah. Right. We got 3 more in this lesson. We'll probably finish this tonight, and then binary trees, I don't know if we'll get that done tonight. Maybe, we'll see. Might try and power through. It's lesson 10, and then we've got, if we get through this and this, 1, 2, 3, 4, 5, 6 left, blimey. It's going to be at least another session or 2 on this. Another live stream or 2. How's everyone doing out there? You have a good time? Busy doing other things? Chilling? Do I need to get background music for this stream? Will that help? Will that make it more entertaining? Let me know. Let me know in the comments. Remove from head. We're one method away from having a fully functioning O1 queue. We just need a way to remove the first element from the linked list in constant time. When we're finished, our linked list will fulfill the basic requirements of a queue. Add to tail, constant time insert. Remove from head, constant time pop. Let's rename the linked list class to LLQ and remove the add to head functionality because queues don't allow inserting it into the wrong end. We've also flipped the arrows in the printed representation to reflect the change. So assignment, complete the remove from head method. It should remove the first node from the list, the head, and return it. If the list is empty, just return none. So if self.head is none, then return none. Then the head should point. The head should point to the next node in the list if there is one. The tail should point to none if the list is empty now. The old head's node should no longer be pointing to anything. So the head should now point to the next node in the list if there is one. The head should now point to the next node in the list if there is one. The tail should be none if the list is now empty. The old head's node should no longer point to anything. The head should now point to the next. Hold on. If the list is empty, just return none. The head should now point to the next node in the list if there is one. Like, it should remove the first node from the list. It should remove the first node from the list. Okay. So the head should now point to the next node in the list. If there is one. So I guess it is how do I remove it? Complete the remove from head method. It should remove the first node from the list, the head, and return it. Right, so just return self dot head. Is that it? That can't be right. Nope, didn't think so. Hmm. It should now point to the next node in the list if there is one. Node in self print no node but it wants to be 01. What we're trying to learn linked lists. But it needs to be 01, so I can't loop through things, so I can't do that. What's the deal? I don't understand like this. So if the list is empty, just return none. That's easy, we just done that. The head should now point to the next node in the list if there is one. Should point to the next node in the list. So is it self dot head equals self dot next? Is it like, yeah, self dot next? Tail should be none if the list is now empty. Okay, self dot tail equal to none. Old heads node should no longer point to anything. So self dot head self dot head, what is it dot set, and it's got next none. The head should now point to the next node in the list. Head should now point to the next node list of the part I can't get. So the tail should be none if the list is empty now. So I did that. If the list is now empty after that. So return remove old head. So then old head equals self dot head. And then we're saying head should now point to the next node in the list if there is one. Head points to self next, yeah. And then the tail should be none if the list is now empty. Okay. So check again. So if self dot head is none, then tail should be set to none. So then self dot tail is equal to none, and then all heads node should no longer point to anything. That's confusing as heck. The head should now point to the next node in the list. So this part. So next node of the list, if there is one. How do I check if there is one in the next, like in the list? The tail should be set to none if the list is now empty. So if this got set to none, if the list is now empty, the old heads node should no longer point to anything. So old head set next, none, that pretty sure. So the head should now point to the next node in the list if there is one. Head should now point to the next node in the list if there is one. So how do I do that? Should now point to the next node in the list. Let's go next. Self, I don't know, like -1 or something? No? Do I say nodes equals... Oh, I don't even know. Hold on. Right, I'm gonna ask Boots again. I'm stuck again. How do I get the next node in the list? Killing me, Boots. I see your code and output. Let's work through this together. Think carefully. In a linked list, each node has a next property that points to the next node in the list. If you want to move the head of the list to the next node, what attribute would you Oh, is it just... Oh, I'm a big dum-dum that I missed that. I know. Right, let's read it. Think carefully, blah, blah, blah. If you want to move the head of the list from... If you want to move the head of the list to the next node, what attribute can you access from self.head to get that node? Try exploring a line like this, self head. Oh, just overwrite it. Like I was doing before, I just missed the... Oh, doofus. Ah. Alright, it is late here. I'm starting to show. Okay, we'll finish linked list definitely, and then let's have a look at binary trees when we get to it. So, yay, it's just a quiz now. Linked list queue quiz. Let's recap a few key points about linked lists and queues. The problem with our array, normal Python list, implementation of a queue is that was that it had an on push operations. The linked list implementation of a queue has O1 push operations. Linked lists are usually a worse choice than standard arrays because they are less performant due to more memory overhead. They are more complex to work with, debug, and reason about. They have no random access indexing a specific element. Doubly linked lists are a better choice than arrays in very specific circumstances because they have O1 insertion and deletions at both ends of the list. A queue made with a linked list instead of array uses less memory, is simpler to implement, is faster to search through, can have O1 pushes and pops. That one. Another question? Yes. Another question to finish it off. A queue that uses an array doesn't have O1 pushes and pops because when elements are added or removed from the last index of the array, all items need to shift, which takes O of n time. When elements are added or removed from the first index of the array, items need to shift, which takes O. That one raised too much memory and arrays are slower. It's because, yeah, you have to shift everything along when you put things into the middle and whatnot. Or blimey. 15. I think this might be a tomorrow one. I think we're going to start now. I'm going to get sucked in and, I'm not going to want to stop. So there might be some tricky ones in there. So I think we'll leave it for tonight. Yes, that'll be the ideal. So let's stop now. So, thanks for coming down tonight. If you had fun watching, let me know. If you didn't have fun, let me know as well. I'll try and improve the streams going forward, make it a little bit more entertaining, but I am learning here. So it is a little difficult to be as entertaining while I'm actually trying to use my brain. So, and get things stuck in there. But anyway, hope you've had a good night. It's been fun streaming and stuff. Feel free to follow, leave some more comments and stuff. All the favorite from you guys. Just loads of fun. If you're coming back from the future because you're watching a live stream afterwards, let me know where you get your time machine from. And